Hello friends, this is a short video in which I'm going to talk about the important formulas that's going to come for Neet exam for the chapter Kinetic Theory of Gases. So we start with the perfect gas equation or the ideal gas equation. Comes in two variants, PV equals nRT and PV equals nkBT. The first case, so we have the number of moles, that is small n, and then capital N, which comes with the Boltzmann's constant. It represents the number of atoms. So wherever R is going to come, we have the number of moles, and wherever Kb comes, we'll have number of atoms. So we have to keep in mind of this trend. And then how the kinetic energy of a molecule is related to the temperature. And we can say that the total internal energy of the system is expressed in terms of the kinetic energy. The kinetic energy contributes to the internal energy. And we are going to talk about the monoatomic system and diatomic system. What is the internal energy or the total kinetic energy of a system? For a monatomic system, it's going to come with 3 degrees of freedom. That is 3 translational directions, and for each we'll have half kBt, so we'll have in total 3/2 kBt, or we can also say that 3/2 RT. If you talk for the diatomic system, it's going to come with 5 degrees of freedom, the 3 translational and 2 rotational degrees of freedom. So we can say 5/2 kBt and 5/2 RT. And so this kBt, wherever kBt come, we know that it represents the molecule. So this 3/2 kBt is the mean kinetic energy per molecule, and 3/2 RT is the mean kinetic energy per mole. Okay, so we have mole and molecule. So the pressure, in terms of kinetic theory, the pressure is defined as 2/3 times internal energy divided by volume. Remember, the internal energy used in this expression is entirely dependent on the kinetic energy because of the translation. So we can say that, so the pressure is 2/3 U by V. So this is internal energy density of the medium, and the speed of the gas molecules. So before we discuss about the speed, we need to understand about these two terms, kBt by m. So wherever this kb and small n comes, and with R we have the capital M. So both of these are identical. So kb and small m, the small m represents the atomic mass and capital M represents the molar mass. Okay, so with this definition, we have to understand the formulas for root mean square velocity, maximum probable speed, and average speed. So we can say that, so the Vrms is √3 kBt, √3 RT by m. So the mass definitions changes. Okay, so from kb to R. So we can approximate it as 1.73 √RT by m. And then we have most probable speed, so which is √2 instead of √3. So that will come around 1.41 RT by capital M molar mass. Then average speed is, so we can approximate it as 1.60 RT by m. Average velocity for a system is always 0. Okay, so the speed takes numerical values where the velocity on an average be 0. And then the degrees of freedom. Degrees of freedom is represented by capital F. So we have to talk for monoatomic, diatomic, and triatomic system. For monoatomic system, 3 translation degrees of freedom, 3 plus 2 translation plus rotation, 3 plus 2 plus 2, 3 translation, 2 rotation, and 2 vibration. So we can have for mono, diatomic, and triatomic 3, 5, and 7 respectively. So specific heat capacity. The specific heat capacity, the first relation is Cp minus Cv equals R by N, where N is a number of moles. And gamma, so the adiabatic factor Cp by Cv, it is relatable to the degrees of freedom by 1 plus 2 by F. So once you know the degree of freedom for the diatomic, monoatomic, and diatomic system, we can say that. And also one application of the gamma is, it is related to the speed of sound through a medium, gamma RT by m, where m is the molar mass of the gas that's formed in the medium. And then, so using this definition, we can approximate gamma as 5/3, 7/5, and 9/7. Okay. Finally, mean free path. Mean free path is related as 1/√2 pi sigma square n, where sigma is the diameter of the molecule and n is the number of molecules per unit volume. It is the number density. And finally, mean free path is directly proportional to temperature and is inversely proportional to pressure.